Again, it's a great pleasure to be back here. Okay. So, let me begin by giving the motivation for this talk. It will be just one slide motivation. Okay. So, the idea is that in quantum field theory, the analyticity properties of the S matrix follow from locality of the theory. Unfortunately, string theory does not have a description as a local quantum field theory. So, the question that we will try to address is, does the string theory S matrix share the same analyticity properties as local quantum field theory? Okay. And we will see that the answer is yes as far as we can tell, okay, but there will be some questions left open. So, let me set up the problem. Okay. So, we will consider a scattering amplitude of n particles. We will denote the momenta by Pa. Okay. So, each of them satisfy their on shell condition, okay. And I will take all the particles to have positive mass, strictly positive mass. Okay. So, no massless particles for now. I will come back to this point later. Okay. And the convention will be all momenta will be counted as ingoing. Okay. So, outgoing momenta will have negative energy, for example. Okay. And the notation for the metric is mostly plus. So, Pa square is minus Pa 0 square plus Pa vector square.
Sorry, what did you say you will come back to?
The fact that we are taking the masses to be strictly positive.
You mean you will consider tachyons? Is that
No. Zero mass particles are the issues.
Strictly.
Yeah.
Sorry.
Yeah.
Got it.
Yeah. Tachyon. I am not going to talk about tachyons. Yeah. No. Yeah.
Sorry.
Okay. So, we define the center of mass energy, okay, SAB, okay, as this. So, which you can expand in terms of Pa dot Pb. And the question that one would like to ask is, in what domain in the complex SAB space is the scattering amplitude analytic? Okay. And this is the usual starting point. Okay. Once you understand this, then this is the usual starting point for studying many other properties, like for example crossing symmetry, dispersion relations and so on. Okay. Once you understand the domain of analyticity of the S matrix. So, let me begin by discussing how this is studied in local quantum field theory. Okay. And here we found that this book is a very good starting point. Okay. This book has almost everything that you want to know about analyticity properties in quantum field theory. Okay. This is not the old Bogoliubov Sirkov, but it is somewhat new book, I think written in the mid 80s. Okay. So, let us consider the off shell amputated Green's function, which I will denote by G. So, the LSG prescription tells us that the S matrix is given by G evaluated on shell. Okay. This is off shell Green's function, but S matrix is G evaluated on shell, and here I am ignoring the wave function normalization factors because those are just constants multiplying G. Okay. So, those you do not worry about right now. Okay. And the other point is that in writing this you have dropped the Lorentz indices, but that is just notational convenience. So, you can always attach Lorentz indices here and Lorentz indices here. So, let us take any subset of these n particles, which I call A alpha. Okay. This subset could also include single particles, okay, but not empty set or the full set. Okay. It could involve single particle, two particle and so on. Okay. And we denote by P alpha the sum of all the momenta Pa in that subset. Okay. So, of this n particles we just divide it into two subsets and take P alpha to be the sum of momenta of that subset. Now, what one can show, and this is based on the locality of the position space Green's function, which basically means that it uses the fact that the commutator of two local operators vanish outside the light cone. Okay. So, based on this, one can show that this function, the Green's function, is analytic in the following domain. Okay. So, domain is given as follows. So, if imaginary P alpha is not 0, okay, then imaginary P alpha must be time like. Okay. If it is 0, okay, then P alpha momentum, okay, must be below the threshold of production of multiparticle states in the channel A alpha. Okay. So, this is the condition. So, what one can show based on just local properties of the position space Green's function, okay, is that the Green's function is analytic in this domain.
For any choice of little n, right? You subdivide.
Yeah. So, any choice of A alpha. Okay. You subdivide this n particles into any subset. For any subset, this condition has to be satisfied. Either if imaginary P alpha is 0, then it must be time like, or if it is 0, then it has to be below threshold. The real part has to be below threshold.
Presumably there are also some analyticity properties of non-amputated off-shell Green's functions.
These are all off-shell Green's functions.
Oh, so this is the answer for the off-shell Green's?
Yes, for the off-shell Green's function, not for the S matrix.
Oh, not for this. So you've not yet set P square is equal to M
No, no.
Okay.
So it will become the G if P square equal to M square. Okay, so this property is proved purely for the off-shell Green's function, just based on the locality.
What happens for the when the imaginary P alpha becomes space like?
Okay, typically the based on just the position space, the analyticity of the locality of the position space Green's function, you cannot prove anything about what happens when it becomes space like.
No, I mean the other condition, for example, one can say because of the multi-particle.
Multi-particle states. Yeah, for this condition it's not very physical, but it's just that I mean this is what you can prove just based on the locality.
But it could be even analytic.
It could be even analytic outside. Okay, we will see a little more of this as I go along. Okay, what you could say. So this is the statement. Okay, so the Green's function is analytic in the domain. Either imaginary P alpha is not 0. Okay, in which case it has to be time like. Sorry, it has to be time like. Okay, or if it is 0, then the real P alpha. Okay, P alpha is real, and that has to be below the threshold. So, we will call this the primitive domain of analyticity. Okay. Now comes the disappointing news, okay, which is that one can show that this manifold, the primitive domain of analyticity, okay, has 0 intersection with the subspace in which the external states are on shell. Okay. That there is no common point between this primitive domain of analyticity and this subspace. Okay, the proof is elementary, so I will go through the proof in the next slide.
So, why is imaginary part of P alpha playing such an important role? Why imaginary rather than the real part?
Okay, because you start by writing down the momentum space Green's function as a integral, right? And then the point is the way you try to study analyticity is by showing that the contour can be closed in some direction, right? And there is e to the I p dot x sitting in the exponent, right? So, in order for that to converge, you have to be able to define it, right? That's how this imaginary P alpha comes into play.
The constant is on the square of imaginary.
Yeah, that basically says that it has to be time like.
So, in some frame you have to be able to close it.
Yeah. Okay. See, the point is you use the fact that the commutator vanishes outside the light cone.
Yeah.
Right? So you don't directly start with time ordered product. The Green's function of course refers to time ordered product, right? Okay. What you do is that you start with the retarded Green's function. Okay. So the commutator multiplied by theta, okay, that vanishes outside the light cone. Okay. Then you based on that, okay, you study properties of its Fourier transform. Okay, but that's still a Fourier transform of the retarded Green's function, right? Not the time ordered product. Then you show that on the real axis, okay, when P alpha is real, in some range, okay, in particular in this range, the retarded Green's function and the time ordered product agrees. Okay, that this you do by writing this as a sum over states, intermediate states, and basically this condition guarantees that there are no states in the intermediate. So difference becomes a sum over intermediate state, and there is no intermediate state because of this condition. So you show that the time ordered Green's function and retarded Green's function coincide on some region, and that's enough to show that as long as retarded Green's function has an analytic continuation, time ordered Green's function will also have an analytic continuation.
Sorry, one more question. So, these Green's functions have cuts
Yes.
somewhere. So when you say in P alpha, you have to also do you have is there some specification of which sheet you're on of this analytic function?
Okay, this is the sheet that you get by starting from on the real axis in this region, right, and then just extending the domain.
So like the first sheet.
First sheet, exactly.
It could be much more complicated on the second sheet.
Yeah, it could be because you don't. This statement, right, puts you inside an open set. right? You don't go out of that open set, right? Because of this boundaries that imaginary P alpha has to be light-like, sorry, has to be time-like, right? It's what is called, they call the star-shaped region around the origin, right? So you start with P equal to 0, right? That's the origin, and there is a star-shaped region around the origin in which this analyticity holds, right? So to go to the second seat and all, you have to go out of this star-shaped region.
Because the cut starts.
Exactly.
Some
That's
finite
right.
distance.
Exactly. The cut is not inside this domain,
Yeah.
right?
Because we're dealing with massive.
Exactly. Yeah.
At the thresholds or something.
Exactly. That's right. So that's why this condition is necessary.
So to understand this technically, given a set of momentum, you find all the possible subsets, and for each subset, this condition has to be true.
Yes. For each subset, this condition has to be true. The either imaginary P alpha, if imaginary P alpha is non-zero, then it must be time-like, right? If it is 0, right, then the P alpha square has to satisfy this condition. Right.
For mixed cases, we don't have any statement. Like for some subsets, suppose you have one of them satisfied.
Yeah. So for each subset, one or the other should be satisfied. Right. That for some subset, imaginary P alpha may be 0, right? So for that subset, the second condition has to be satisfied. Right. For some subset, the imaginary P alpha may be non-zero, for which the first condition is what is relevant. Right. So the point is, for every subset, one or the two of the two conditions have to hold. Right. That either imaginary P alpha is time-like, or if it is 0, then the real part, the real P alpha, has to satisfy this condition. Is this statement clear? Okay. So let me give a proof that these two domains don't intersect. Okay. So this is a condition again. Okay. So let's split PA as a sum of its real part and imaginary part, okay, PR plus IPI. Then the initial condition, okay, PA square plus MS square equal to 0 takes this form. Okay. So this in particular means that PAR dot PI must vanish, okay, because the imaginary part has to vanish. Okay. Now it's a general result that if you have two time-like vectors, okay, whether they are forward, backward, doesn't matter, their inner product can never vanish. Okay, inner product of two time-like vectors, if they are both in the forward light cone or both in the backward light cone, then it's negative. If one forward, one backward, it's positive, right? So it cannot vanish. Okay. So that means that both PAR and PI cannot be time-like. Okay, or at least one has to be space-like. Okay. Now you look at the real part of this condition, right, which is here. Okay. And now you see that because at least one of them have to be space-like, that means at least one of them have to be positive, right? Okay. And that in turn means that this must be positive. Okay, because if this is positive, right, then to make, say, left hand side of course is positive, right? So if this is positive, then without anything else you can say this is positive. Okay.
Right.
If this is negative, then by the first condition the other one must be positive. Right. So PI square must be positive, okay, and this is in conflict to the first condition, right, because PI, right, imaginary part of PA, okay, for every set, okay, the imaginary part of PA has to be time-like. Okay, and this says that for the set containing a single particle, okay, imaginary part of PA is space-like. So the only possibility is that all the PAs must be real, right? So this you have to rule out now, right? All the PAs real. If all the PAs are real, that means all the P alphas are also real, right? Because each P alpha is a sum of the subset of the momenta. Okay. But now it's impossible to satisfy the second condition, right? P alpha cannot be below threshold, because once you have certain number of incoming particles coming in, right? So that sum, you can always produce those particles in the final state, right? Just by energy momentum conservation. So you fail to satisfy the second condition, okay? And this basically means that analyticity of the primitive domain is useless. Well, at least apparently, that the analyticity of G in the primitive domain is useless for exploring analyticity properties of the S matrix. Okay, but fortunately, this is not the end of the story. Okay, that's why we are saying this. Is this okay so far? Okay. So the way out, okay, is based on some properties of the function of many complex variables. Okay, this does not work for function of one complex variable, but functions of many complex variables. Okay. So, suppose we have a function of several complex variables, okay, and suppose we know that it is analytic in some domain D. Okay. Then depending on the property of D, okay, often without knowing anything else about the function, we can prove that the function is analytic in an extended domain D prime. Okay. So, D prime depends only on D and nothing on there is no information about F, right, except that F is analytic in D. Okay. So, this is different from what happens in for function of single complex variable. Right. For a single complex variable, you can consider functions which are analytic inside a given domain, okay, and admit no analytic continuation. Right. There is a singularity all along the boundary. Right. This is like the Young-Lee edge singularities of that kind. Right. You have a domain, the function is analytic inside the domain, but it cannot be continued outside. Right. Everywhere on the boundary there is a there are poles. Okay. This cannot happen for functions of many complex variables. Okay. That it is, well, not that it can never happen, okay, but often depending on D, one can show that there is an extension which is D prime. Is the statement clear?
Wait, so for a function of a single variable, I mean, if I have the simple ones like 1 over 1 minus z.
Yeah, but you cannot specify the function. You can only say the function is analytic inside some domain.
Without knowing, I see.
Right?
Without knowing what f is.
Yeah, without knowing what a function is.
I see.
So, of course, there are all examples of functions which are analytic in some domain and that can be extended. Right? But this is without knowing the function. Okay? You only say that you have a function which is analytic in a domain D. Right?
So here, if I have a function of two variables like z1 and z2, which is analytic inside the disk or whatever the complex version of that is, then I can just extend it.
Well, not disk, but to some domain. You can construct domains, right? See, in the case of function of single complex variable, right, you cannot consider, there is no domain of this kind, right? You can always find a given any domain.
Right.
You can always find examples of functions which are analytic inside the domain and not analytic outside. Okay, I mean, because every domain can be mapped to a disk, right? Every connected domain can be mapped to a disk. Right? And then you can use the example of Young-Lee edge singularity, for example, right, where it has singularity everywhere on the boundary. Okay? These modular functions are like that, right? E to the 2 pi I tau, right? Or when we express in terms of q equal to e to the 2 pi I tau, right? On mod q equal to 1, that basically is the end of the boundary, right? It's like the function is defined, or in tau variable it's defined on the upper half plane. It's a perfectly analytic function on the upper half plane, but it gets blocked. You cannot extend it to the lower half plane.
So is the extension always non-trivial? I mean, the domain D prime, is it always?
No, so in some cases D prime may be the same as D, right? But that whether it is the same as D or not depends only on D and nothing else. That's the statement. Okay, so I'll elaborate this with a simple example. In fact, these extensions are done by not by very sophisticated mathematics, but by simple Cauchy's integral. Okay, so here is an example. Okay. So let's suppose that you have a function which is analytic in the union of two subspaces d1 and d2. Okay. What is d1? So it's a function of two variables. So d1 is an annulus in the z1 plane times a disk in the z2 plane, okay, and d2 is the reverse. Okay, it's an annulus in the z2 plane and a disk in the z1 plane, right? So in picture, if one of them is like this, so you exclude this region, okay, times this, the other one is the opposite. You exclude this region. Okay. Then one can show that it's analytic in the product of the two disks. Okay, there cannot be any obstruction to analytically continue the function over the whole product of the two disks. If you know that the function is analytic in this domain and in this domain, okay, then without knowing anything about the function, you can conclude that it's analytic in this domain, the product of these two. This is a bigger domain than this one, right? No excluded region.
So just to clarify, at least on analysis, the partial derivative with respect to Z1 bar and Z2 bar should be 0.
Yes, yes, exactly. Partial derivative with respect to Z1 bar and Z2 bar should be 0. Okay.
And you can allow, will you allow like isolated singularities, like pole type singularities inside these regions? Or it's really
No.
strictly?
It's strictly analytic, nothing. So here is the proof. Okay, I mean that's basically the end of the proof. Okay, it's 2 lines. So here is the construction, right? So let's suppose that you have Z1, Z2 inside D prime, any point. Okay, so you define G Z1, Z2 as this contour integral. This C lies inside this region. So basically you are defining this as a contour integral where the contour lies inside this. Pardon? Z1 is any. Z1 is anywhere, yeah, because zeta 1 is what you need, right? Zeta 1 contour lies there, Z1 is anywhere. Okay. So this contour integral is well defined, right? There is no divergence anywhere. This is perfectly well defined. Okay. We are doing this integral here. Furthermore, you can show that this function G Z1 Z2 okay, coincides with f in this domain. Okay. Well, you don't have nothing to show, because in this domain, right, this one can be shrunk, right, and by using Cauchy's integral formula, that you know that it's equal to f Z1 Z2. See, here it cannot be shrunk, right? Okay. But if you take Z2 to be in this,
So you are saying take Z2 also to lie in the angular.
yeah, so
Then they will agree.
exactly, then they will agree, right?
Correct.
So that means you have now identified a certain region,
I see.
right, in the Z1 Z2 space where the two functions agree, f and g agree.
I see. And then here you extended in.
Yeah, here you could use Cauchy's integral formula, right, to shrink the contour, right, pick up the residue. Okay.
I see.
So that basically shows that the G okay, agrees with f when this is in D2, and hence G must be the analytic continuation of f. Okay. G is perfectly well defined, right? It's perfectly analytic everywhere in the over the whole disk.
So if it was already disk cross disk,
Then you cannot extend it. Yeah. Okay. So basically, it uses certain convexity property, right? The domains of analyticity okay, can be extended okay, if it's not convex.
So it fills out the holes.
Yeah, it basically fills out the holes, right? And that's basically all there is, that you define holomorphic surfaces and try to, if the holomorphic surface goes out of the domain, right, then you can extend it in those regions.
but the holes have to be in this kind of, I mean, in the sense of what I'm saying, that if it was like annulus cross annulus, then what would you do?
Yeah, then you got, well, yeah, so therefore you need this, you have to be able to close this.
Yeah.
Right?
Nice.
So there are general tricks by which you do this extension, right? That as long as there is a holomorphic domain, right, that you can extend, which goes outside this, right, you define the contour integral outside in the region where it's well defined, right, and using that you can extend it everywhere where the disk has gone out.
So the same proof will work even if in D2 both of them are disks.
If in, yeah, because that of course is yeah, see, this is the same as this, right? The domain in which you are extending is this one, right? So the initial domain was this union this, right? That had some things missing, right? And you have extended it to the product, right? Which has basically filled all the holes. Okay. So basically the idea is that this domain, the primitive domain of analyticity that I described, right? That has lots of holes like this. Okay. And using that you can actually extend the analyticity proof of the Green's function outside those domains. Okay, so that's the basic trick, that even though just based on the locality, right, and integrals, okay, convergence of integrals, you got only a small region, right, the imaginary P alpha in the forward light cone. Okay, you can actually extend it.
And
Okay.
is the final condition, maybe this is too simple as the union of all the domains in which the function is initially defined has no holes in it?
Well, yeah, but that has no holes is a somewhat, I mean, yeah, a vague thing, right? And I think the full domain is not known. Okay, people have basically studied in the old days of axiomatic field theory. People studied bits and pieces, right? And they proved various results. Okay, but what is the maximal domain in which it can be extended, right? That's not known. Okay, but even by extending this, they managed to prove many interesting things. Okay, that just by this trial and error extension.
But, sir, even roughly, I can't understand the analog. But your original domain was basically P. Imaginary part of P was
Exactly, and so it was going like this and then going like this, right?
So the whole is like the space-like region.
Yeah, exactly. That's right.
Ah.
Right. So you extend it in the space-like region, right? That's why it starts including the on-shell.
Multiple sets which play the role of this union, right?
Exactly. Yeah. Yeah. Exactly. Right. So basically, the idea that if you have things like this, right, and you fill part of this region, okay, how much you fill depends on the details, right? I mean, that depends on also how clever you are. I mean, as I said, I don't think the maximal extension that is possible is understood, right? But people have done a lot of work to extend it as much as possible.
But here the whole is non-compact, so that doesn't matter.
That doesn't matter, because as long as you can use the Cauchy's integral formula, right? See, you have to basically draw a circle in this region, right, to define the integral. Okay, and then the disk extends through the hole.
So how do I draw the circle here?
It's like this. See, this is a cone, right?
Oh, okay, I see.
So somehow, yeah, and the point is there are some part of the space-like region that is included, right?
Right.
So they are clever ways of drawing the circle, right, which actually extends outside.
Maximal region of analyticity in physical space is, I mean, the one that is identified is known to be the maximum in the physical
No,
space.
no,
Even
even that is not known. I think so. What is the maximal domain of analysis of the S matrix? I think it's still an open question. Right? What people have done, as I said, based on this, you derive various results, right? But it's not complete. Yes.
So, does proof require us to consider these multiparticle subsets or single particle subsets?
No, see, the proof doesn't care about any refer to the particle physics at all back, right?
So, I mean,
It's
you took subsets of this 1 to n indices.
yeah. So the proof includes multi-particle subsets. Yeah. Okay. Most of the work has been done in the 2 to 2, right? So there, of course, it's there are not too many multi-particle subspaces, but there are also some work, like for example, crossing for multi-particle scattering. There it uses multi-particle subsets.
So, to show that the primitive domain of analyticity does not overlap with the on-shell guys, we just needed to consider single particle subsets.
Exactly. That's right.
But to extend it, we need
You need a multi-particle. Exactly. Yeah. You need the full dome. I mean, the full set of conditions. Exactly. Okay. So here are some examples which people managed to prove based on this, right? One is the crossing symmetry, right? Basically, you look at these two processes. Okay. Now, as far as Green's functions are concerned, it's clear that they refer to the same Green's function, right? It's only that the range of P1, P2, P3, P4 that is relevant for this is different than the range of P1, P2, P3, P4 that is relevant for this. Okay. And so the statement of crossing symmetry is that there is an analytic continuation from this domain to this domain. Right. So this is what was proved by these people. Okay. They basically found appropriate domains, right, that extrapolate, then interpolate between these. Okay. And those domains lie totally inside the on-shell space, on-shell subspace. Right. That's important. You don't go and do the analytic continuation through off-shell Green's function. Right. You start with the off-shell Green's function, you extend the domain, right, which starts intersecting the on-shell subspace, and then you have to show that in the on-shell subspace there is a domain that interpolates between these regions.
So that would just, I mean, that would be saying that it's analytic, but the fact that they are equal is not what is.
See, the point is, if you think of Feynman diagram, right, and it can do it in more generally, then it's the same Feynman diagram that calculates this and this, right? So now the question is whether, so as an analytic function they look the same, right? it's the question is whether there is actually an interpolation, right, whether the function has non-analyticity in between, right. So, even though they look the same, there is no connection, right. So, that is the worry about the crossing symmetry, right. So, functions.
Does it matter whether one can interpolate between the two or not in an analytic fashion?
Oh, the statement of crossing symmetry is that you should be able to interpolate between the two as an analytic function. Okay.
Why was it important that you finally have to do the interpolation staying in the physical region?
Because you want to do it for S matrix, right. See, ultimately you want to get rid of the Green's function and you want to think of this as an analytic property of the S matrix.
Suppose you got a gauge theory, you were scattering electrons.
Yeah.
It's only the S matrix that is physical.
You can fix a gauge, you can prove all this, right. But at the end, you want to make a statement about the S matrix.
But it could be your gauge dependent.
Yeah, it could be gauge dependent, exactly.
Has spurious singularities. And
Exactly.
You don't want to depend on that.
Yeah.
I see. No, but I meant, as you were saying, if you do the calculation in Feynman diagrams, it looks the same. But the issue is there could be some, singularity when you continue.
Exactly. Yeah.
Now, if even without going through just the physical region, you showed that the function is analytic, that would be.
But that could be a gauge dependent statement, right. See, the off-scale Green's functions are different in different gauges.
I agree. But if in some gauge you could have proved this, then in that gauge you would have.
Yeah, but okay, normally that is not what people call analyticity, right. When you say crossing symmetry, right, I mean you always try to refer back to the S matrix, right. Even though you use Green's function, right, that is where the locality came in, right, because it is not clear how to use directly locality to S matrix, right. So, you go through the Green's function, so locality to Green's function to S matrix, but ultimately you want to make a statement only on the S matrix.
And I would actually be worried about the converse thing, that there were spurious singularities in the Green's function.
You could introduce spurious singularities if you want, right.
Which would prevent, I agree. I was just wondering logically if you could do it for something. Yeah, I understand.
Is there any interesting statement to make about large time equations?
Large.
Large time equations.
Largest time, yeah. Okay, largest time equation is used for unitarity proof, right. As far as analyticity is concerned, it is not directly used, the largest time equation. But when you show that the Green's function is analytic, right, it is in the same spirit, right, because you are starting from some property of the position space Green's function, right, and then you are trying to prove a property of the momentum space Green's function. Right.
Knowing that these things are analytic in the bigger domains,
Yes.
and then going back to that equation, can we say something, some positivity of certain things?
Well, see, largest time equation implies unitarity,
Yes.
right,
Yes.
cutting rules, right. I mean, I do not know what else you want to get from there. I mean, for that you do not need this, right.
For example, at finite temperatures, you might like to prove that you only get decay instead of growth.
Okay, this is all at 0 temperature, right. So, I do not know whether one can actually use it at finite temperature combined with largest time equation, because largest time equation will mean that you have to go back to the position space Green's functions, right.
Yes, yes.
Whereas here the advantage is they have already come to momentum space, you are making a statement directly on the S matrix.
Yes.
And Ashok, suppose we for a moment allowed massless particles,
Okay.
then the first statement you said about analyticity of these Green's functions, that remains true or not? The primitive.
No, that does not remain true, because what happens is that there is no gap, right.
Yeah.
We will see where things go wrong for massless particles.
Okay.
Okay, so we will discuss the massless particles in a few minutes. Okay, so now we come to the question to superstring theory, okay, and ask what we can do here.
Sorry, one more question. Suppose you have no massless particles but long range forces.
Okay.
Would this theorem continue to work?
You mean long-range forces because of explicit non-locality?
I'm thinking of matter like Chern-Simons theories, where
Chern-Simons,
Chern-Simons
yeah.
mediates long-range forces, but there are no really massless particles, so there would be new massless states on non-trivial manifolds. In such a situation, would you be able to prove analyticity or not?
Yeah, maybe one can, and I am not completely sure, right, because the commutators vanishing outside the light cone probably will still be true, right.
Yes.
and using that, I mean, that's what they use basically to prove these results in the momentum space.
Sorry, when you say there are no massless particles, you mean just in this n particle scattering process, right?
No, even in the intermediate process, even in the, we'll see, even in the intermediate state, right, if there are massless particles, there are issues, right. So we'll discuss that in a few minutes.
But it might be that the fact that there are boundary excitations will I think there's experimental evidence that these S matrices are not
The crossing, yeah,
not crossing
yeah.
symmetric in these theories. So
Maybe the point is one can, I mean, directly identify where the non-analyticity is, right? One can go back and see where the arguments break down.
Okay, yeah.
Right? That may be the
Yeah.
most effective way to address this. Okay. So the idea is that we want to extend this in superstring theory. Okay. So first we need, if you want to use the same approach, you need off-shell Green's function. Okay, so that you can calculate using superstring field theory, because that is an off-shell formulation. Okay. So the goal will be to prove analyticity of G in the primitive domain, the same primitive domain that we had for field theory.
I'm sorry to keep interrupting, Ashok,
Yeah.
but say you're in a gauge theory, this off-shell Green's function, would you attach the Wilson lines or you just allow it to be gauge?
No, you are to get, as I said, gauge theories are massless particles, right?
So you won't.
Okay. So you will not directly address gauge theory questions, but what you can do is you fix a Lorentz gauge,
Yeah.
right? You can fix a Lorentz gauge, then you put a mass term. That you can always do, right? Because you have gauge fixed anyway. Okay? If you are in larger than 4 dimension, right, you keep the mass terms non-zero till the end, okay? And then you can take the mass terms to 0. And we know that because there is no infrared divergence, right, it will reproduce back the actual S matrix elements. But for study of this analyticity property, you have to keep the masses non-zero.
Exactly. So suppose you did the same for Chern-Simons theories. You could formally do the same thing. Go to Lorentz gauge, add a mass term, and then the question is whether there's an infrared effect as you take M to 0.
Exactly, that's right.
But that's precisely the anionic phase.
Yeah,
Okay, that's not
it could be, yeah, that,
Yeah. Okay.
there could be a problem there, right?
Yes, yes.
So that's why, I mean, see, in 4 dimension, you don't expect S matrix to make sense anyway for
Yes.
gauge theories, right?
Yeah.
So it's not clear what you mean by analyticity property of the S matrix. Right? In hard dimension, S matrix does make sense, right? But nevertheless, it will have non-analyticities, right? Not in the form of divergences, right? But like x to the 10 log x is still non-analytic at x equal to 0. Okay? So you basically what you do is that you keep the log x's away from x equal to 0, right? So that you have some domain of analyticity. Yeah, add a mass term, right? And then you say that you have established analyticity of something that is not quite what you want to calculate, but its m goes to 0 limit, okay, is well defined, and it's what you want to calculate. Okay, so that's the best you can do in the presence of massless particles.
Sorry, I should know this, but even in 4D for abelian gauge theory also there is no S matrix.
No, because once there are charged particles, you have infrared divergences. Right, so that's
Not very singular ones, but you see.
yeah. But the point is the way you avoid, I mean, the one way to get rid of this is you work in terms of cross section, right? You have sum over soft emissions in the final state, right?
Another
it's
way,
that issue.
but another way might be these fuzzy coolings.
Yeah,
right?
yeah. But I think that
That's another whole.
yeah, that it's a. I mean, it has not been developed to the extent that one can
There's
actually
no unitarity
do this.
equation in that form,
Exactly.
right?
Yeah, yeah.
I should get an education, I see.
Okay, so the idea is that we want to prove this, because if we can prove these properties, right, then we don't have to do anything. We can just take all the results that the axiomatic field theory people have derived and we can lift it to superstring theory, right, because their analysis, okay, was only based on complex functions, right. Once they have established that, once they start with the fact that the Green's function is analytic in the primitive domain of analyticity, okay, after that they only use the theory of complex functions to prove their results, right. So the result will just directly lift to superstring theory if we can prove the analyticity of the off-shell Green's function in this domain.
So I mean, just to understand, for the field theory, you used causality properties of vanishing outside the light cone to come here. Here you are saying we'll just prove this directly, and then you'll be on track to.
Exactly. Yeah. Okay. So, the strategy will be to, so the point we do not have the position space Green's functions because those are highly non-local, okay. So, that is not a good starting point. So, we will try to prove it directly using Feynman diagrams, okay. So, that is the strategy. Okay. So, now a few words about superstring field theory, you do not really need to know too much. Okay. So, the first thing is that it has infinite number of fields which I will denote by phi alpha. Okay. Its action is complicated, but the key feature of this action is that the kinetic term is more or less standard. Okay. So, this is a gauge fixed action. So, the kinetic term is more or less standard, this k alpha beta is quadratic in momentum, okay. No higher derivative terms in the kinetic operator, okay. But the interactions, okay, have very complicated vortex. This is the interaction written in the momentum space. So, these Vn's have complicated dependence on momentum, they are non-local, non-polynomial. Okay. But what will be important for us is that these have exponential suppression factors, okay, for large momentum. Okay. But large momentum means that we have to have the 0 components approach plus minus I infinity and the spatial components approach plus minus infinity, okay, because basically it is like e to the minus k square, that is the kind of suppression, okay. E to the minus k square, that means k0 square comes with a positive sign, right. So, you need to go to plus minus I infinity. Okay. So, because of this, each Feynman diagram is manifestly UV finite as long as the ends of the k0 integrals are at plus minus I infinity and the ends of the spatial integrals are at plus minus infinity. Okay. So, basically you have to tie up the ends at for the spatial integrals, momentum integrals at plus minus infinity and the loop the energy integrals at plus minus I infinity.
Ashok, maybe you said this, but in this there will be massless fields.
There will be massless fields. I have not said it yet. We are going to get rid of the massless fields. Meaning we have to somehow get rid of the massless fields to do anything here, right? Because that is true also in QFT.
Yes.
Right. So, the main purpose is to, okay, so let me go back to the motivation again, right. The main motivation is to check if string theory has additional problems, okay, with non-analyticity than quantum field theories. Okay. The problems that are there in quantum field theory, we expect them to be there in string theory as well, right. So, the massless particle problem is there in quantum field theory, they will be certainly there in string theory. Right. We want to see if string theory non-localities introduce additional complications.
So, you will use the same regulator mass.
Exactly, yeah.
There's no equivalent of tachyon among these fields, right?
No, because you are using superstring field theory, so you do not include tachyons. If you have tachyons, then things are much more complicated. That we will see why, I mean as we go through the analysis.
There are no position space analog of correlation functions that we can.
No, because of these exponential factors, right, when you try to take Fourier transform, it becomes very complicated. So, there is nobody has really gotten a position space analog of these correlation functions.
So there are the commutative minus sharp side that is.
Exactly, yeah. I mean at least not in the covariant formulation, right. In the light cone formulation there is some understanding, okay, but all the axiomatic field theory results are based on covariant, they use the fact that the Green's function is Lorentz invariant and in fact invariant and complex Lorentz transformation. Yeah, so, those will all be lost if you try to use light cone field theory.
And any position space things in string theory would be highly gauge dependent, right?
Yeah, yeah. Of course, momentum space things are also highly gauge dependent.
Right. But at least you know exactly what to do to get to the gauge.
Exactly, yeah.
Namely, what you just replace all the
Go on, Shel.
Yeah,
Oh,
on sale, go on sale, exactly. Okay, so now I come to the infrared issues, okay, which I have been discussing. So, the point is that in the presence of massless states, S matrix has infrared singularities. Singularities does not always mean divergences. The infrared singularities are present in all dimensions. Okay, as I said, x to the 10 log x is singular at x equal to 0, right, even though it is perfectly finite. Okay. But this kind of analysis that we will be doing will declare x to the 10 log x as singular at x equal to 0, right, because it is non-analytic. Okay, that is what we are studying. Okay. So, we need either subtraction or regulation, you can use either. So, let me just explain what we mean by subtraction. Okay. So, subtraction will basically mean that we replace each internal propagator by 1 minus p times the propagator. So, we basically introduce a projection operator which removes the massless fields, right, which basically says that we will be doing loops of string field theory, but we will remove all the massless fields from the intermediate state, right. So, you will get something which is not really the S matrix, but you can call it some kind of effective action where the massless fields still have to be integrated, okay. And the analyticity property you are going to prove is for this effective action, okay, where the massless fields have not been integrated out, okay. And the idea is that the massless fields will produce same kind of singularities as in a normal quantum field theory, right. So, I mean, you don't worry about that, right.
But the internal propagators for the massive fields will go down to whatever zero momentum, so to say.
Yes, yes, exactly.
It's not a RG kind of thing.
No,
It's
no, we are just removing the massless fields. In fact, this is a natural subtraction because one can show that this kind of effective action satisfies some BV master equation, right. So, there is a, even though it is not gauge invariant of course, right, but you can keep track of the gauge invariance because it satisfies an appropriate BV master equation, right, which tells us that you can extract gauge invariant quantities from this effective action.
But even though the massive fields are going down to zero momentum, because they're massive, I mean, isn't it more or less a Wilsonian effective action? Because zero momentum anyway carries mass because they're massive.
Yeah, I mean the point is you also have to integrate out the high momentum modes of the massless fields. Here you are keeping the full.
More relevant. But I mean, okay, conceptually you're right. I mean, if you were constructing the effective action, you would have to integrate the high momentum modes and stop the integrals for the massive fields.
Exactly, yeah. So, there is a way to integrate out the high momentum modes here, right. I mean, in the vortex itself, you can introduce, I mean, there is a ambiguity in choosing the vortex, and by appropriate choice of the vortex, we can also make sure that among the massless modes, right, the high momentum modes are integrated out already. So, this is one way you can remove the massless modes from internal lines. Okay. The other one, as I said, is just regularize. After you have gauge fix, you just add mass terms for the massless particles. Okay. So, this will be free from infrared singularities, okay, because everything is massive, and you can analyze analyticity of this amplitude. Okay. And if you are in dimension larger than 4, it is guaranteed that the regulated amplitude will approach the actual amplitude when you take the zero mass limit. Okay. So, you prove analyticity of something, okay, and that analytic object in the m goes to 0 limit produces the correct S matrix.
What happens to the domain of analyticity in the m going to 0?
It gets pinched basically, right. So, the thresholds, I mean, so exactly. So, if you look at the domain of analyticity, right, I mean, it gets cut basically in this limit, right. So, crossing symmetry for example requires any smooth interpolation, right, between one channel and another channel, right. You find that region gets pinched into two distinct regions.
But you still have a non-trivial result for a domain of analyticity.
Yes, yeah, you can still have a non-trivial result for the domain of analysis, exactly, because you do it for non-zero mass and then you take the mass goes to 0 limit. Okay, so the net upshot is that we will now proceed assuming that there is no strictly zero mass particle in the theory. Okay. So, we will begin by analyzing the Green's function at the origin. So, when all the external momenta are 0, okay, we can just take the loop energy integration contours just along the imaginary axis, okay, and the spatial components along the real axis. Okay, that will be my prescription for how to define this Green's function at 0 momentum. Okay, so I am not talking about Feynman diagrams. Okay, now from now on, it will be just analysis of Feynman diagrams. And I take an arbitrary Feynman diagram, take all the loop energy integrals to run along the imaginary axis, all the loop momentum integrals to run along the real axis. Okay. So, in this case, if we take an internal propagator with some momentum L, okay, L0 will be imaginary and Li's are real. Okay. So, L square plus m square is strictly positive, right, because it is minus L0 square plus L square plus m square. This is positive, so it is strictly positive, and there is no problem in defining the integrals. Okay. So, this basically shows that the Green's function is analytic in the neighborhood of the origin. Is this clear? Right, because in the neighborhood of the origin, if you just take the contour straight up for the energy and along the real axis for the momentum, everything is well defined.
And you are saying neighborhood of origin because the actual momentum will be L plus P for instance.
Exactly, that is right. Okay, so, if you take P to be too big, then this is not true anymore. here you can see the role of M, right. As long as M is non-zero, there is a finite neighborhood of the origin where this is true, right, because M will save you, right, even if there is an L plus B. Okay. So here is a distribution of poles in a complex K0. So K, okay, so I should just say this once and for all. So in my notation K, okay, or Ks will denote the loop momentum, independent loop momentum, okay, and Ls will refer to the momentum of individual propagators, right. So Ls typically will be linear combination of the Ks and the external momentum, right, that's the notation. Okay. So in the L0 plane we have the poles L0 equal to minus L square plus M square, L0 equal to plus L square plus M square, but in the K0 plane, okay, these poles are shifted along the imaginary axis, okay, because K0 is L0 plus some additional loop momentum, right, from other loops, right, they are flowing. So in the K0 plane the poles will be distributed like this.
This is still keeping all the external
Momentum 0, exactly. Okay. The important point that I want to note here, okay, is that the positive L0s, okay, lie on the right of the integration contour and the negative L0s lie on the left of the integration contour. Okay, so this will be important as we go along. Okay. So now if we start deforming the external momenta away from 0, the pole positions will start moving. Okay, it will not be symmetrically situated like this. Okay. And the idea is that if the poles approach the integration contour, okay, it may look like the integral is becoming singular, okay, but we can still move the integration contour away from the poles to avoid singularities like here, right. Instead of taking the K0 along the imaginary axis, if the poles come from this side and this side, we just deform the contour, okay, we can still define the integral, there is no singularity because you just avoid the poles. So the integral becomes singular when the contour is pinched by poles from two sides. Let us imagine that there is one pole coming from this side, one pole coming from that side, right. Then you cannot deform the contour anymore, okay, that is where the integral becomes singular. So when you are trying to analyze whether the integral, the Feynman integral is singular or not, okay, we have to look for conditions that the contour is pinched by poles from two sides. So we cannot move away from the pole by deforming the contour.
Sorry, Ashok, I didn't understand one thing. Is there a significance to avoiding the first pole by going this way and the other one?
It depends on from which way it is coming. If it is coming from the right, you have to avoid by moving left, right. So you can never let the pole cross the contour, right. You are analytically deforming the function, right. Yeah. So if the contour is like this, right. Yeah. And suppose the pole is coming like this, right. Then you have to deform away from the poles, right. When you cannot deform away from the poles, that is where you hit the singularity. So basically the idea will be to show that this kind of pinch does not happen as long as the external momenta are in the primitive domain. Right? That will be what you want to prove, that you can always deform the contours away from the singularities.
So you can only use properties of only propagate the singularities in the integrand occur only in propagator.
Yes, but the ends have to be fixed at plus minus infinity, right. So that also has to be.
So the only real input of string theory is the ends.
Exactly.
Otherwise,
Yeah.
this is a Feynman diagram.
Yeah, it is a Feynman diagram. Okay, except that in the field theory, one does not know how to prove. I mean, at least it was not known how to prove this for Feynman diagrams, right.
And the rule for where the ends are is different in field theory or not?
Typically, it is different because you weak rotate, right.
Yes.
In field theory, you just put everything on a real axis, right, with the I epsilon prescription. But that eventually does not play too much of a role.
Okay. Because whether it was here or not, you could still locally come on this
Yeah,
way, right?
exactly. That's right. Okay. So in a sense, you can think of this, okay, also as an alternative proof
Of field theory.
in field theory based on Feynman diagrams,
Yeah.
right, not based on locality.
Because what matters is just a collision of poles, right?
Exactly. That's right.
No matter how they
Exactly.
That's what I wanted to ask. I mean,
Collision of poles, but if the two poles on one side collide, it doesn't matter, right? It's the collision of poles from opposite sides.
sorry if I can ask just about the field theory, I mean, in string theory you have these vertices which are very soft.
Yes.
And that's why you keep the endpoints fixed, etc., which you don't have in field theory.
That's right.
So,
So in field theory, typically you have to add counter terms to remove infinities, right? That problem is not there here. In field theory, you have to do a little more work because these UV divergences, right, whether they can interfere, start interfering with this, you have to worry.
Yeah. Or are you suggesting another way to add irrelevant operators in field theory?
Yeah, see, in this procedure, you can certainly do in field theory also, keeping the ends fixed at plus minus I infinity. Okay. But nevertheless, it will not be, the integrals are not finite by themselves, right? You have divergences and you have to add counter terms to remove those divergences in a field theory. Right? Most likely they will not interfere with this kind of analysis, but that's an extra work that you have to do in a quantum field theory, which you don't need to do in string theory.
Yeah, but you can do this analysis in the theory with the counter terms.
Yeah, exactly.
And then this part doesn't seem to care about that.
Shouldn't, yeah. I mean, naively at least it shouldn't care about the theory of the counter terms. Okay. Now, what we have been able to prove, okay, we have not been able to prove it for the general, most general case, right, and that's where the string theory and field theory differ, not that they actually differ, but we just haven't established this result. Okay. So, what we have been able to prove is a limited version of this result, okay, when the imaginary PA lie in a two-dimensional plane. Okay. All the imaginary parts, okay, lie in a two-dimensional plane. Okay. A more Lorentz invariant way of stating this is that all the imaginary parts are just linear combinations of two independent vectors. Okay. Under that condition, you have given this proof. Okay. Fortunately, if we go back to the literature on S matrix, right, everything that people have done, okay, only uses this limited result. Okay. Nobody has been able to make use of the result, okay, of this more general analyticity of the full Green's function to extract some useful property of the S matrix. No, even for multiple particle scattering, right, what they do is that they, when they prove crossing, for example, right, they find paths, right, each of which uses deformation, partial deformation, right. So that's why at every stage, right, you only allow two momentum to be deformed. So from that point of view, whatever result is known about S matrix, right, holds also for string theory. Okay, but it is possible that one can derive more results for S matrix in field theory, right, which you cannot prove just based on this. Okay, so I will try to explain now how we go about proving this. Okay, and this will be to all orders in perturbation theory. You don't need to restrict to any given order in perturbation theory.
Sorry, this is a basic question, but in field theory, if you use some sort of a regulator, exponential decay momentum space of a vortex, which will allow you to lock the contours that way.
Yeah.
Then as you take the regulator to 0, does one get sensible answers?
Well, see, what you can do probably is that you can, this analysis is dimension independent, right. So you can probably do a dimensional regularization. Suppose you work in 4 minus epsilon dimension, right, in field theory. Then probably you can, use all of these results, right. So you can prove this analyticity in 4 minus epsilon dimension or d minus epsilon dimension. Right. The exponential regulator, I don't know what happens.
I mean, that's like string scale, as
Yeah.
the string scale to infinity, right, to get to the field theory of 0 modes.
Yeah, you see, if you do this calculation in string theory, right, then you can translate the result in terms of field theory, right. It will be, there will be derivative expansion. You can write it as a low energy effective action, right, as a derivative expansion. So that you can certainly do, right. So from that point of view, you can make sense of this. Instead of thinking of the regulator going to infinity, you just think of that it's a momentum expansion, right, momentum going to 0.
Then you have an infinite number of counter terms.
Yes, they have infinite number of derivatives, exactly. Yeah. So from the field theory viewpoint, you are adding infinite number of counter terms.
About Abhijit's exponential regulator, if you modify the propagator so that it decays exponentially,
Yeah, it's possible. But in a sense, okay, if you modify the propagator, you can always probably absorb those into vortices, right?
Exactly. But suppose I do it so that I modify the propagator.
Okay.
Nothing funny is happening with the vertices. That might be convenient
Okay.
because it just is replacing the propagator by another analytic structure.
Okay.
Which is
Okay.
Yeah, also then it will be automatically non-perturbative because you are doing only something to the propagator part and not to the interaction. I mean, just like the RG equation, it's just exact.
Yeah.
This is what Kuczynski does in his exact renormalization
Yeah.
of equations.
Yeah.
All the regulator stuff is only
In the propagator, yeah. Yeah. Yeah, unfortunately here, I mean, you don't know of anywhere to move all the exponential factors to propagators, right? Some of course you can move, but after you have moved, for example, from a 3-point function, right, there will still be exponential factors remaining in the 4-point function. So it's not true in string field theory, everything can be moved into propagator. Okay, so let me now give some details of the analysis, how we go about proving this. Okay. So we do it in 2 steps.
So you're going to do it for that first primitive condition. Is this right?
For the
There were two analyticity conditions. There was a primitive analyticity condition and then an extended one.
yeah, extended one we don't have to do,
Yeah.
because that whatever axiomatic field theory people have done, right?
It works even though you will prove a limited primitive condition.
Yes, that's what I said, that all the what they had used, right, is only this limited condition.
I see. They start with a limited primitivity condition and then they get their full analyticity condition only using that limited primitivity.
Well, they are full meaning, see, we don't know what the full analyticity condition is,
Whatever
right?
they get.
Yeah, whatever they get,
Yeah.
right, they only use this limited result, right, where basically at most 2 independent imaginary parts, right? All imaginary parts are linear combinations of 2 vectors. So that's the reason why, I mean, as of now, right, this is general enough to prove all the results on S matrix that you know for quantum field theories. Okay, so the way we prove this is in 2 steps. Okay, so let me see how far we can explain. Okay. The first step we should be able to explain in detail. So the first step is to keep the imaginary parts of P1 0, okay, and deform all other components of external momenta from 0 to the desired value. Okay, and we will do it remaining inside T. So in the first step, I will illustrate it diagrammatically in the next slide. So in the first step, we just keep the P1 real, okay, but P0 imaginary part we allow it to deform. Okay. So in this case, only the PA0s have imaginary part, and we will show that we do not encounter any pinch singularity during this deformation. Okay. In the second step, we deform the imaginary part of P1a from 0 to the desired value. But at this stage, we keep all other components fixed and we remain inside T, okay, because all other components have already been deformed to whatever the desired values are.
I'm sorry, in the first part, you're keeping only P1, imaginary part of P1 fixed.
0, yeah.
Zero. And P2, P3, P4 can be deformed. The imaginary part can be deformed.
No, no, P2, P3 are not deforming anyway. See, because you are, see, the upper, so these are the components, right? Because you are already taking imaginary PS to be in the 0, 1 plane, right?
Good.
So P2, P3, P4 are already 0, even in the final point.
Oh, I didn't know.
Okay.
0, 1 plane.
This is in space time.
In space time, yes.
So in the 0, 1 plane, they can have non-zero imaginary parts, right? What am I saying?
Yeah. So P0 and P1 for all the external states can have non-zero imaginary part, right?
Yes.
So in the first stage, we only deform the P0s,
Okay.
right? Leave the P1s as they
Now
are.
I understand. Sorry.
We deform the P0s, but also the real parts, right? From the origin. We start from the origin, right? That's why the things are well defined.
Actually, when you say P1, you meant space-time one, not
Space-time one, yes, not particle one. So yeah, so that's the lower. So the particle index will not play any role, right? It's a space-time one. Okay. So in the first step, we deform everything, okay, to the desired values except the P2. Except the P1, imaginary part of P1, right? All the real parts are deformed to whatever they are supposed to be, and the imaginary part of P0 is deformed to what they are supposed to be. So most of the deformation takes place here, okay? But this is the easy part of the analysis. In the second stage, as I said, we deform the P1 imaginary part of the P1s from 0 to the desired value, because they are 0 kept 0 in the first stage. Okay. And during this deformation, we keep everything else fixed.
In this, sorry, you will say this of course, but this is the trickier part because your exponential factors are softened as long as the P's are all real, the P1s are all real, and here you are changing.
No, see, exponential factors depend on the loop momentum, right?
Sorry.
So, loop momentum are kept fixed anyway at the two ends.
You don't want to deform this imaginary part too much, right? Because then it would become a space.
Exactly, yeah, exactly. We have to go inside the D. So, basically, this deformation you always have to remain inside D. Right? We don't want to go outside D. That's you have to make sure that all these deformations are done remaining inside D, and during the deformation you have to show that you don't encounter this pinch. Right? So, that's the strategy.
Sorry, I mean the D was that the imaginary part was time-like, right?
Exactly.
So, but the imaginary part here, you are not deforming P0s at all.
No, P0 has been deformed already in the first stage.
Okay. In the later, this is the second step.
Yeah, in the second step, P0s are already non-zero and time-like, that they are non-zero, right? Now you are deforming P1, right? You don't want to deform the P1s too much, right? Then they will become space-like. Okay, in the first stage they are only along the time direction, right? So there is no confusion about this being time-like, right? Everything is time-like in the first stage.
So is the statement that if we exceed the domain D, then pinch singularity would certainly happen? Or
No, then this proof breaks down, right? Not that it will certainly happen, right? In fact, it cannot be that it certainly happens, because you know that it can extend the domain somewhat, right? I mean, after all, that's how we proved analysis of the S matrix. So it will certainly not certainly happen, but it can happen. So that's the correct statement. Okay, so this is basically the schematic representation, that if you take the imaginary P1A, P0A, then the first stage we just deform the imaginary P0A and also everything else. Okay, that we need to define. All the real parts are deformed, and in the second stage we only deform imaginary P1A.
And when you say time-like, there was no condition whether it's in this or that.
No, it can be either forward or backward, doesn't matter. Okay, so this is the goal, right? We deform, so as we are deforming the components of PA, right, we have to keep deforming the contours. Okay. Now, to establish that there is a singularity, okay, we have to establish that there is no way to deform a contour to avoid the singularity, right? But to establish that there is no singularity, okay, we can decide how we want to deform the contour, right? It is up to us. There should be a way to deform the contour. Okay. So, we choose that way, okay, by saying that all the spatial components of loop momentum, right, which to begin with are along the real axis anyway, okay, they will be kept along the real axis. Right. We are not going to deform the spatial components of loop momentum at all. Okay. They will be running on a real axis, but the time component will deform. Okay, we have to deform, in fact, because the poles will eventually come and approach the singularity. Okay. And what we will try to show is that this KS0 contours are never pinched during this process. Okay, if we can prove this, then we have established the absence of singularity. So, to prove this, we will assume the contrary, that they are pinched, and then show that there is a contradiction.
S is the label for the loop.
S is the label for the loop. Exactly.
in practice, how complicated is the motion of these poles as you form?
In general, it is complicated, right?
It's not just parallel to the real axis, not that simple.
No, because the point is that you are also deforming the other loop momenta, right? So, a given loop momenta gets fed by the external momenta, also the other loop momenta, right? So, in general, it will be a complicated motion in this plane.
So you only concentrate on the pinching part. Whatever happens,
Exactly.
pinch it, then
Exactly. So, you have to show that it is not pinched, right? So, as I said, we will assume that there is a pinch and then show that there is a contradiction. So, let us suppose that you have hit a pinch singularity, okay, during this deformation. Okay. So, the first time when you hit a pinch singularity during this deformation, certain internal propagators are forced to be on shell due to pinch, right. That is the meaning of a pinch, that some poles are, you cannot deform away from some poles, right, by K0 contour deformation. So, we associate with this pinch a reduced diagram. Okay. So, this is basically obtained by shrinking to point all propagators that are not forced to be on shell at that point. Okay. So, for example, if you have a Feynman diagram like this, say box diagram, okay, and we say that these two poles come on shell. Sorry. Okay, let me draw it here. That suppose there is a Feynman diagram like this, okay, and we say that these two poles become on shell, right, at the pinch. These are not on shell. So, you basically shrink these 2 points and think of this as a diagram like this. So, this is the meaning of reduced diagram, right. You postulate that some certain poles are forced to be on shell, okay. Everything else you shrink to points to get a reduced diagram.
Even though there may not be originally a vertex.
Yeah, there may not be originally a vertex, but that does not matter.
Because these are the only possible sources of non-analyticity.
Exactly, these are the only possible sources of non-analyticity, right. So, then by definition, by construction, we are saying that it is impossible to deform the K0 contours away from these poles, right. That is the meaning of a reduced diagram, because these are pitched. Okay, we may still be able to go away by deforming the other contours which are kept fixed, right, along the real axis, the spatial momenta, but that is not relevant now. Okay, we will show that this does not happen. Okay. So, now the propagators of the, let us take the propagator of a reduced diagram, right, which are all on shell, right, which means that if L is the momentum carried by a propagator, okay, it satisfies this condition, right, on shell condition. Okay. So, now we will draw an arrow along L if we pick if the pole corresponds to the positive number, and we will draw an arrow opposite to L if we pick the negative number, right. And there is a clear distinction because this is along the real axis. The L vector is, those are all real, right. So, there is no confusion about positive and negative poles. So, here is an example of a reduced diagram, right. I have drawn a, so that means that we have said that these poles are all, these propagators are all forced to be on shell, okay, and at that point the energy flows this way, right, along the arrows. Now, the claim is that the arrows in a reduced diagram cannot form a closed loop. Okay. This is what we will prove.
Sorry, can I see the definition of the arrow once more?
Yeah, arrow is basically giving you the direction of energy flow, right. See, the propagator is on shell,
Okay.
right. So, the energy is either positive or negative because the spatial momenta are all real anyway,
Okay.
right, and you are just drawing the arrow along the energy flow. So, here is a claim, the arrows in a reduced diagram cannot form a closed loop. So, this is not an allowed reduced diagram because here you can see there is a closed loop, right. Okay. The proof goes as follows. Okay. So, let us take, suppose that there is a closed loop like this, okay, and K is the momentum that is flowing along the loop. Okay. Then the propagators, right, that are along the loop, okay, their momentum is given by K plus LR, where LR is determined by the external momentum and other loop momentum, right, whatever is flowing through the vortices. Okay. Now, we notice that for at the origin, okay, the positive L0 poles are to the right of the K0 integration contour, right, that was from this picture over here. At the origin, the positive L0 were to the right of the integration contour, negative L0 is to the left of the integration contour, right. And we are assuming that this is the first time we are hitting the pinch, right. So, no pole has crossed the contour till now. So, this means that all of these poles are to the right of the K0 integration contour, right. and these are the only propagators on which depend on k.
Then you can move.
So you can deform the k0 contour, right, away from these poles, because all the poles are to the right. Right. So this is what shows that you have to have that you cannot have closed loops along the arrows, right? Because as long as you have a closed loop, you identify the loop momentum along the loop, okay? And then you show that all the poles are on the one side of the integration contour for that particular loop momentum. Is this clear?
So now that means this diagram can be further reduced.
Exactly. You basically shrink this loop, right? Because okay, and then you apply the same argument on the rest of the diagrams. Okay, so this is what I have already said. Okay.
So when we shrink this loop, the L2 propagator is also shrunk.
Exactly, because once you deform k, right? We had said that to begin with all of these are on shell, right? Now you deform k in one direction, right? You move away from all the poles, right? So all the propagators are shrunk.
But how about this other loop that L2 is involved with?
Well, for fixed value of that momentum, you have deformed k away, right? So that basically says that the original pinch point, right, is not this reduced diagram, but the reduced diagram where this loop has been shrunk. Okay. So the net upshot of this is that ultimate reduced diagram, right, after you have deformed the k0 contours in the possible ways, okay, that it cannot have any loop along which the arrows are unidirectional.
So now you will increase the p's, the external momenta. So this was the argument with external momenta equal to 0, but then again
No.
you have the small neighborhood universe.
No.
Sorry, I'm getting.
Okay. We started from there,
Yeah.
right, and then we said that we start deforming, step 1 deformation, right?
Ah, yes.
Okay.
Got it.
So now, because that's why the pinch can occur, right? Okay. And what we are showing is that you cannot have a pinch where there is a closed loop, right? You can have a pinch where there are no closed loops, right? But you cannot have a pinch where there are
Depending
closed
on the
loops.
external momenta is that movement of the.
Exactly.
Yes.
That's right.
Sorry, Ashok, I understood that you can't have this closed loop, and then how did you go after that?
Yeah. So I have not gone very much after that. So yeah. So after this is the statement, right? That if there is no closed loop, okay, then one can show that the vertices will admit partial ordering, so the arrows flow from left to right. Okay. So this basically is a simple example in graphs. Basically, if there is no closed loop, right, that means that there has to be one sink and one source, right? Because suppose there is no sink, every vertex has something going in, something coming out, right? Then you can keep going, right? And there are finite number of vertices, right? So you will eventually come back to the vertex that you had started, right? So there has to be a source, right? And similarly, going in the opposite direction, you can show that there is a sink, okay? And then you can delete the source and the sink, right? Repeat this process again, okay? And that basically shows that the vertices can be ordered, right? The source you put on the extreme left, the sink you put on the extreme right, okay? And you can order the vertices this way, so that all the arrows flow from left to right.
So a source and shrink in what you were describing is a vertex where all arrows are outward directed or inward.
Exactly, right? So the vertices where all the arrows are inward directed, you put on the extreme right, right? You draw it that way, and the vertices where it's outward directed, you put on the extreme left. Okay? Then you can delete those vertices and then repeat the analysis again, right? Again, the rest of the vertices you put one to the right, one to the left, and so this is a partial ordering, right? Not every pair of vertices may have an ordering, but you can do a partial ordering where all the arrows are from left to right. Okay, so I have given an example here. So this is an example of a reduced diagram, okay, which has no closed loop. See, it's clear that if there is a closed loop, you cannot have an ordering of the vertices like this, right? Because the loop has to turn back. But here, the vertices can be ordered so that all the momenta flow from left to right.
Partial ordering, because there could be multiple.
Yeah, like between these two, for example, right? You can draw this to the left of this or the right? It doesn't matter. Okay, whenever there are two vertices that are connected by an arrow, by a line, then the ordering is fixed. right, but there may be vertices which are not connected by propagators. Okay. So, once you have a partial ordering, right, now let us just draw a vertical line, okay, which cuts some of these propagators. Okay. So, across the vertical lines you see the total momentum that is flowing from left to right is one of the p alphas, right, something that is entering from the right. That is the sum of these momenta of these lines, right. All of these are real because these are all on shell, right. L0 is square root of L square plus M square, all of these are real, right. So, the first condition obviously is violated, right, imaginary p alpha is 0. So, you have to check the second condition, right, where it is below threshold or not, and just from this diagram it is clear that it is not below threshold, right, it can just produce these particles, right, by momentum conservation. Okay. So, basically this shows that we are outside the domain D. Because these lines are all on shell, right, these are lines in a reduced diagram. Yeah, these are all on shell and is the spatial momentum we have kept real, right. So, that is why imaginary parts are all 0.
Here
Right.
you use that in P1 is 0.
Exactly. I use the fact that in P1 is 0, exactly.
In P1 is 0. In
The
Pi
spatial parts we are not deforming at all, right, in the first stage.
P0 is determined in terms of all the others, and if they are all real, then it's right.
Is this okay? Okay. Now, unfortunately, the second part is the one which involves most of the work, right. This was like epsilon compared to the second part, but I will try to just give a very brief overview of how we did this. Maybe okay, but the point we did for us it was like this was epsilon and the rest was 1 minus epsilon, but maybe for explaining this it will not be that bad, right. Let's see how far you can go.
You're going to say the rest is 1 by epsilon.
No, sum is a 1. That's the normalization. Okay, let's see. So, the second stage is to deform the imaginary p1s, right. Okay. But this is being done. So, we are deforming them from 0 to the desired value, but we now want to keep all the other components of PA fixed. So, we will choose the integration contours for the loop moment. Again, it is up to us how we choose the integration contours, right, as long as you can show that there is a way to avoid the pinching. Okay. So, this time we will keep the k2 to k d minus 1, the second to d minus 1th component, these will all keep real. Okay. Keeping k1 real does not help, right, because external momenta are imaginary anyway, p1 components. Okay. So, the k1s contours will be allowed to be deformed away from the real axis, but the ends of course have to be kept fixed at plus minus infinity. Okay. And this part which requires some explanation, that as we deform the k1s contours along the imaginary direction, the k0 contours are kept fixed at the end of step 1. See, at the end of step 1, right, we have gotten some k0 contours, right, which avoid singularity. Okay. Those will not move anymore. Okay. In the case 1 was running along the real axis, okay, we will just let the KS1 contour go up and down, okay, deform it along the vertical direction. Okay. But for given real KS1, we will keep the KS0 contours exactly identical, okay, no change at all.
And you said you can still get away by keeping all the other spatial contours.
Exactly.
So that is already great simplification. Right?
That's
you don't
right.
have to think about all that.
Exactly. So, you can work at fixed values of those,
Yeah.
right, you do not have to even do the integral, right, work at the fixed values of those, and so that you can do this deformation. Yeah, imaginary part is 2-dimensional problem.
And then you will explain it, but is it required? Does it require essentially similar type of arguments as before? Because
It's similar but not quite the same.
It's not the same because now 0 is some complicated
Exactly. 0 has already been deformed, right? Okay. So, now before we start deforming, okay, let us examine the configuration that you have gotten at the end of step 1, okay. But this time we are going to examine it from the point of view of the case 1 integration contours, right. Earlier we were doing it in terms of case 0 integration contours, right. The same poles, now we are going to look at it from the case 1 plane, case 1 plane, okay. So, in the case 1 plane, right, let me explain this here. Case 1 was being integrated on the real axis, right. So, let us fix some value of case 1. Okay. So, for this particular value of case 1, the case zeros, right, or case prime 0, all the case zeros, right, those were some contours, right. So, if you now think of the location of the poles, the case flows along certain loops, right, certain number of, these are the k, this is the k, certain number of poles depend on the k, right, they are momentum depend on k, right. So, they are the ones which are going to contribute in the case 1 plane, okay. So, as you vary the case zeros, right, those are some curves in the case 1 plane, okay. So, what you are plotting here, this figure, okay, is that, so they are poles like this, right, contours like this, okay. What you are plotting here is that you go vertically up, okay, pick the lowest one, the one that comes closest to this. Is that clear? We know that it cannot come all the way here, because we already know that you have avoided the pole at the first stage, right. So, the contours have been chosen in such a way, the case 0 contours have been chosen in such a way that we avoid coming right on top, right, because the poles are away from the real axis, okay. But the poles come sufficiently close, right, somewhere along this. So, that is what we plot. So, that is what this diagram, okay. The one that comes closest on the top, one that comes closest from the bottom at the bottom.
All these curves are poles in the K1S plane.
In the K1S plane, exactly.
As a function of K0s.
No, no, not as a function of K0s. As you are varying K0s, right?
The locations are
Locations are where the whichever one comes at the closest, right? The reason that there is a discontinuity, right? That like this, right? Here, for example, as you vary, right? Here, this one is the lowest, right? So, the contour will follow this curve, and then from here on, this one comes lowest.
this is the envelope of
The envelope, exactly, right? Okay, so this we can call the singular loci, right? I mean the ones that are most dangerous, which are coming close.
And sorry, does this depend on how far you deformed in the K0 plane?
Yes, because the K0 contours are of course not uniquely fixed,
Yeah.
right? So, depending on how you deform the K0 plane, these things will vary,
Yes.
right? But you are saying that let us suppose that you have chosen some K0 contours, right? Once you have chosen them at the end of step 1, you are not going to deform them again,
Okay.
right? We just keep them fixed,
Yeah.
and based on that we do this study. Okay. Now, let us collect the set of propagators through which Ks flows. Okay. So, those are the only propagators which can give rise to pole in the Ks plane. Okay. So, typically if we take Lr as the momentum carried by say one of the propagators in this set, okay, then Lr will have the form of Ks plus some capital Lr, where this is the linear combination of the external and other loop momenta. Okay. That is the general structure. And in the Lr variable, the poles are at these positions. This is just L square plus M square, or Lr square plus Mr square equal to 0, right. Earlier we were thinking in terms of L0 as a function of the rest, now I am thinking of the L1 as a function of the rest, right. That is what this represents. Okay. And the second line is just the Lr part expressed in terms of the Ks. So, the point that we want to see here is that at the poles Ks1 and Lr1, right, which is this, they have exactly the same imaginary parts, because these are all real at the end of step 1, right. At the end of step 1 we still haven't deformed the L1s in the imaginary direction, right. All the external momenta have no imaginary part, right, along the one direction, internal momenta are all real, right. So, no imaginary part. So, KS1 and LR1 have exactly the same imaginary parts. So, again if you go back to this diagram, this says that on the upper curve, right, we do not know where which pole gives the lowest contribution, but what we know for sure is that on the upper curve imaginary L1R is positive because this is 0, this is positive. On the lower curve this is negative because this is negative. Okay, this is a trivial statement because these are the same, right. At the end of step 1 imaginary L1R and imaginary K1S is the same.
Sorry, at the end of the step 1, only the 0 component was imaginary.
Exactly.
So this is 0, right?
Okay. See, this is the K1S integration contour that was running along the real axis, right.
Yes.
But this is the location of the poles.
Where it's singular. If you move the K1, where would you hit this?
Exactly. If you move the K1, right. So you have left the K1.
Can you just go back to the last transparency?
Yeah.
So why is it that the imaginary, I didn't get that, imaginary part of KS1
Yes.
and LR1 are the same, is it?
Yes.
Okay, so just let me, I'm sorry.
Yeah.
I didn't fully-
Okay.
External side is 0.
Because external ones have no imaginary part.
Oh, at the poles LR,
See, like this, right.
oh, I see.
Take a complicated diagram, right.
Okay.
If you look at the K here, right.
Yeah,
So L is K plus something flowing from outside, right.
yes, yes.
Okay. At the end of step 1, right, the external momenta are all real for along the one direction. The internal momenta are all real along one direction, right. So, this capital LR, right, which is what is flowing into the loop from the vortex
Is real.
is real. The one component is real.
So therefore KS1's imaginary part will be the same.
Will be the same as LR.
L.
Exactly.
But how did we get the imaginary part for K1?
How did we get?
Yeah.
Oh,
Previous step, did we get it?
no, no. The K1 was going along the imaginary axis, along the real axis, right?
Yeah.
But we get the imaginary part from here. Look at this equation, right? L1R, see previously with the integration contour is along the real axis, but you are asking where are the poles, right?
Okay.
So it's not that we are actually going there,
Yeah.
right?
How far you could.
How far you could go,
Yeah.
right? That's what this is saying.
Got it, okay.
Okay. Yeah, so this is still at the end of step 1, right? Now we start deforming the external P1s, right, and also the L1s inside each loop, okay, in the vertically up and down direction. Okay. So what's going to happen is that during this deformation, okay, these poles are going to get shifted, right, because L1R has now acquired imaginary part, right. So that's going to push the poles up and down, the capital L. The important point is that if you look at the L1R, okay, where the poles are in the as a function of the variable L1, okay, they are completely unchanged. You see, this depends on the transverse momenta, right, the L2 to LD minus 1, which we are keeping fixed anyway, right, and it depends on the 0 components, right. Those contours also we are keeping fixed, right. During the second deformation, those we are not changing. So in the L1 planes, in the variable that for individual propagators, okay, the pole locations are not changing, right, because these pole locations are determined by other components, right, and all the other components are remaining fixed. Okay. But the pole location in the K1 plane is of course changing, right. In the K1 plane it is changing because this is now acquiring an imaginary part. Right. K1 is L1 minus capital L1. Okay. So because of this in the K plane, K1 plane, these things are going to come up and down. Okay. at this stage you can still deform it, right? We still have a choice of K1 contour avoiding the pinch, as you can see, for a while, exactly.
So, Ashok, I mean, if they collide, these envelopes collide, that is not necessary. That also is not necessarily an issue, right? Because the values of K0 are different, right? This is plotted as a function of K0 or not?
Yes, it's plotted as a function of K0, right? But these correspond to different poles, right?
Yeah.
Yeah, so it may or may not be an issue.
Yeah, may or may not be.
Exactly, okay.
Because
But
it could be a
we'll assume this is an issue and then show that it doesn't exist, right? Yeah, so you are saying that it may or may not be an issue, right? Let's suppose that this is an issue, right? So that's in the next one, right? Here, at least what we were doing earlier couldn't be done, right? That if these two happen at the same K0 value, then we are stuck.
Sorry, if you can just go back to the next one. So just so I make sure, little l is the momentum along every propagator.
Along every propagator.
Ks is the
Loop momentum.
for the Sth loop. And your point is that where that L1R is of course determined by the pole condition.
Yes.
So of course it doesn't depend on anything else like capital L per se.
Yeah, not anything else along the one direction, right? Which are the only things that are being deformed.
Okay,
Right.
in the one direction.
Because L1 is determined in terms of the other variables.
Yes, exactly. But K1S is little L1 minus capital L1,
Yes.
and then because capital L1 will have various.
We'll have acquiring imaginary part, right? Both from the external momentum as well as the other loop momenta are getting deformed.
So therefore K1S will change.
K1S will change, right? So these things will move up and down in this plane.
Okay. I see. Okay.
Okay, L1 values will remain unchanged. Right? Okay, so this is a pinch, possible pinch, right? May or may not be a pinch, but at least at this stage you can no longer claim that you can deform the take the contour through. But if this happens, we remember that on the upper curve, imaginary L1Rs are all positive, right? Because we started from here. Remember here, this was a trivial statement. The imaginary L1 is 0 if imaginary K1 is 0. That means on these curves, imaginary L1s are all positive. On these curves, imaginary L1s are non-negative. Right? Because the imaginary L1Rs are not changing, right? They remain positive on the upper curve, they remain negative on the lower curve. Even though the K1s are, of course, can change, right? This whole thing can happen on the positive side of the imaginary K1. Okay. So what does it mean? Okay. So what this shows that if we want to hit a singularity in the K1S integration contour, then at least a pair of propagators along the loop must have opposite values of imaginary L1R, right? At least one propagator, right? So this it's being possibly pinched between these two propagators. One of them must have positive imaginary L1R, the other one must have to have negative imaginary L1R.
For at least one propagator in that loop.
Or at least one propagator in that loop, right? That so they cannot have all the same sign of imaginary L1R. That's what we are saying.
At least two propagators, right? One coming from the one coming from the
Top
is one guy, and the one coming from below is some
another
other
guy.
other.
So the sign has to change,
Right.
right? Okay. So this again means, okay, now we can again assign arrows, right? This time different kinds of arrows. These arrows have no correlation with the earlier arrows, right? So we denote by double arrows. Okay. So if we what we do now is that we assign. Let's see. So we have already a reduced diagram, right, where we have contracted everything else to points. Okay. Now on a given propagator, okay, we assign a double arrow that gives the direction of imaginary L1R. If imaginary L1R is positive, we draw the arrow along L. If it's negative, we draw the arrow opposite to L. Is that clear? That's just an assignment, right? And then the statement that at least a pair of propagators should have opposite imaginary L1, right, means that we cannot have any loop along the arrows. Right? The arrows do not close. Okay. So then by the same logic, okay, now you can say that there is a partial ordering to the vertices for its imaginary L1R flows from left to right. Okay. And that is good enough now. Okay. Now, after this, same just kinematics. Okay, to show that this P alpha now goes out of the primitive domain.
Even though here it's not obvious that they're all real.
Yeah, it's not obvious that they are all real. So we'll see how it comes. Okay. So these are not all real, right? In general, they have imaginary parts. Okay. But we cut again, okay, draw a vertical line, and you have this relation. Right? P alpha is sum over LR with LR square plus MR square 0. These are on shell, and imaginary L1R is positive for all of this. Right?
They're all flowing in the same.
They are flowing in, all flowing in this direction.
That's the problem.
So this basically, okay, so I'll give the details soon, but basically what is happening is, so this means that P, the imaginary P that is coming in, right, is the sum of the imaginary L1s, right. Each of these are on shell, imaginary L1 positive. Okay. So what we will show is that this means that the imaginary P, right, which is the sum of the imaginary L1, okay, that's space like. Okay, and that means that we are outside the domain.
So why is imaginary P sum of imaginary L1? What about L0 was?
Sorry, imaginary P1 alpha.
P1.
Yeah.
But
And imaginary P0 alpha is also there.
is also there. And that could counteract.
That could counteract, yes. So you have to do a little more work.
Yeah.
Okay, let me go here. Okay. So this is our equation, right? P alpha is sum over LR, right? LR is on shell, and imaginary L1R is positive. That much you know, right? Imaginary L0R is something we don't know. But now recall something that we proved earlier, right? When we were trying to prove that there is zero intersection between the primitive domain and the on shell condition. Okay. That if LR is on shell, then imaginary LR must be space like. Okay, this is what we had shown earlier, okay, apart from that condition. So now look at this quadrant L0 L1 plane, or imaginary L0 imaginary L1 plane, right? Imaginary L1 is space like, right? That means it could either lie in this cone or that cone. Okay. Furthermore, we are saying that imaginary L1 is positive, right? That means all the imaginary L1Rs lie in this cone. Okay. So now from the geometry it's clear that if you take the sum of them, right, that's a vector in this cone. Right? That's a space like vector. Right? So that shows the imaginary P alpha is space like. Okay, and hence we are outside the primitive domain. Yeah. So this condition, this is clear that, so this is P is the sum of all the L's. L's are on shell and imaginary L1R is 0, greater than 0, right? Now we are saying that if LR is on shell, then imaginary LR must be space like, right? This is some condition that, let me go back to this old result. Which you are trying to prove for external states here, right? That when there is an on shell particle, right, we showed that the PAI, the imaginary part has to be space like. Right? Any on shell particle, whether it is external or internal does not matter. And that is the condition you are using now, but now on internal states, internal lines. Okay.
And since it's space like at either points in plus x or minus x.
Exactly. Since it's space like, right?
That's a
If you do either, this is 2-dimensional problem, right?
So
Because
just
only
like
Q,
line vector,
yeah,
no.
imaginary P0 or imaginary P1 are only non-zero components, right? So it's so that means it has to lie in this quadrant, right? If it's space like and if imaginary L1 is positive. So this is what breaks down in higher dimension. When you try to extend it to,
You've got an ordering for space like vectors.
exactly,
You don't normally.
that's right, right? Normally the sum of two space like vectors can be light like, right? Here also if one was here and one was there, their sum could be light, could be time like, right? But because of this ordering, right, we know that the sum is also space like.
Where are you using imaginary L0?
Imaginary L0 we are using basically only in this condition.
Okay.
L square plus m square m r square equal to 0, right?
The whole imaginary vector space.
Exactly.
Doesn't matter.
Yeah. Right. So the information about imaginary L0 has gone in, right? I think what he's asking is the imaginary L0 could have been much bigger, right? I mean, why isn't it much bigger? That's because of this on shell condition.
And because the whole thing is space-like, right?
Exactly. That's right.
Yeah.
Okay. So that's basically the end of the proof, right? And yeah, I think this is the conclusion, right? That we, so this basically shows that it's not possible to hit a pinch as long as you are inside the primitive domain. Okay, and hence, at least when the imaginary parts are in this two-dimensional plane, okay, you do not have any singularity inside the primitive domain. I think that's it.
ICTS, any questions?
No, we don't have any questions.
Okay. Note here.
Can you interchange the two steps that you did?
First do L10 and
Step 1 and step 2. Will they come in?
maybe it could be done because L0 and L1 somehow are symmetric. Right? I have not thought about this. Right? So what you are asking is that whether you could have first deformed the L10 part and then L0.
The external moment spatial bar we define.
Yeah, okay. The problem is, yeah, I know what the problem is, that if you try to define the L1 first, right, you already go out of the primitive domain, right, because imaginary parts automatically become space-like, right. That's why you first want to deform the L0, so the P0s, right, so that you go as far as possible inside the domain, and then you move in this direction.
So in terms of this QFT proof, first we are hitting these thresholds.
Yes.
And then we are exploring the cones.
Well, they are in some sense independent because the thresholds are on the real axis, right. The cones are in the imaginary direction, right. So domain of analyticity is part of the real axis, right, and then the cones going out from there.
In the imaginary part of the
Imaginary part, yeah.
Can there be a partial ordering that could be endowed with both the deformations together? Doing this in one step.
Yeah, that's possible in principle, but yeah, it's possible, but I suspect that it will probably become complicated, or maybe one just has to, I mean, think of a clever way of doing it. Right? I mean, it must be possible because after all, I mean, this shows that any contour that you draw, right? I mean, you pick any point, right? You have a way of going there where it doesn't hit pinch singularity, right? That means you can go by any contour, and there shouldn't be a pinch singularity along that contour, right? Because it's free from singularity anywhere inside the primitive domain.
Suppose I said the following. I don't know if it's correct. I'm asking you if this is correct. Since we knew in general terms in quantum field theory that this result was true,
Yes.
then it had to be true diagram by diagram. So some such argument, since you used nothing that was not in quantum field theory, some such argument had to work, right?
Yeah. Well, first of all, I am not completely sure that it had to be true diagram by diagram,
I see.
because in quantum field theory, it's based on the vanishing of the commutator. It's a somewhat indirect argument, right? That you start with the vanishing of the commutator outside the light cone,
Good.
right? Then you, it is, I mean, this shows that it is true diagram by diagram,
It's
right?
true diagram by
But for example, we don't know whether this is true once you go to larger dimensions, right? That when you allow, say, P2, P3 also to be non-zero.
But that's what I was actually going to ask.
Hmm.
I was going to ask that since that is true in quantum field theory, if it's true as a function of a parameter, so it should be true for coefficients of that parameter.
Yeah.
Therefore, it should be true diagram by diagram.
But the point is for any you can say it will be true loop by loop, right?
Yes.
But
but you're saying one, you may have to.
in a given loop there are many diagrams.
I see.
Well, I don't know. I mean, I suspect that there must be a proof somehow, right? That is just that, I mean, those, it's a largest time equation, right? I mean, it's an argument in position space, but of course, we know that it has to have a manifestation in momentum space, right? It's just much more difficult to prove cutting rules directly in momentum space.
Right. So at least for this restricted kinematics, in some sense, the first thing you've done is fill up a lacuna just in the quantum field theory literature, which was instead of relying on some abstract proof, just diagram by
It's a diagram by
you've
diagram.
shown it's true.
Exactly.
And then that proof, basically without change, goes over to string theory.
Yes,
Because you
exactly.
can anywhere
Exactly.
use
Yeah.
the endpoint of the context.
Exactly. That's right.
Okay.
Right? And given that this result exists in quantum field theory for generic external momentum, right, I suspect that there must be a proof, diagrammatic proof,
I think so too.
right, for general external momentum, but it's just that,
Some complicated.
yeah,
Yeah.
yeah, maybe it's not this line of argument at all, right? One doesn't know.
Yeah. There's no counter example. Right?
Yeah.
In quantum field, you have never encountered a counter example of a diagram which is a counter example to the more general analyticity claim.
No. Yeah. I mean, many people have attempted to prove diagrammatically, right? Bjorken and Drell, for example, has a way to analyze diagrams, but basically they again find that they can't really prove anything about the S matrix.
One more vague question. When as a student, when I studied these things in Itzix and Zuber, they made a big deal of these Landau equations, which were the equations that tell you when this pinch happens. You never used.
Yeah, see, those are useful for real external momentum. As long as the external momentum are real, the Landau singularity is a very useful technique for figuring out what the poles are.
I see.
Right? But once the external momentum become complex, basically what happens is alpha parameters, right? They also become complex. Right? You have to deform you cannot go from 0 to 1 anymore.
I see.
Right? And then the nice geometric picture breaks down.
I see.
Right? The fact that some physical thing is happening, right? That's what breaks down.
And one more, again, vague question. I have this vague memory for people studying these two-loop diagrams. Let's say in these like books like the analytic S matrix, and trying to analyze the analytic structure of these diagrams as carefully as they can. And my memory is that they find very complicated analytic structures on the second sheet.
Yeah.
These methods, of course, will have nothing to say about.
No, because this basically identifies a star-shaped region around the origin. That's what they say, right? And they prove analyticity in that star-shaped domain, right? Basically, this says that starting from the origin, you go in different directions, right? But it's an open neighborhood of the origin, right? And you never have another Riemann sheet. The primitive domain of analyticity includes only this star-shaped region.
I mean, why star? I mean, you can always draw a small disk.
Yeah,
inside
so
a
this
star.
according to them is a star. Star means you just go radially out in different directions, right? And the lines end somewhere, that's all.
No holes. Is that
No holes, exactly, yeah. No multiply connected regions and so on.
Does the implication of analyticity, is there one at large values of momenta, either from the primitive?
Yeah, see, the analyticity by itself doesn't tell you anything about the large value of momentum, at least not in this form. Right? That's a separate input that you have to put. For example, to write dispersion relation, you also have to say something about what happens at large momentum, and then you can write some contour integral formula. Right?
No, but you had this first condition where the imaginary part is non-zero, then the imaginary part has to be space-like.
That's right. Yeah. Imaginary part has to be time-like.
Sorry,
Time-like, yes.
And that could then make the momentum. I mean, isn't this saying something about?
Yeah, see, but that is not directly useful, because that primitive domain of analyticity, as we saw, has no overlap with the real momentum, right, with the on-cell momentum. So it's the extension of that has intersection with the on-cell conditions, right? That's
That domain of intersection doesn't go all the way up to infinity.
sometimes it does, right, but doesn't include the point at infinity. It doesn't control the growth at infinity, right. It can, like for example, when you have t equal to 0, right, then you can show analyticity in the whole S plane. 2 by 2 to do scattering, right, forward scattering. For t equal to 0, you can show the amplitude is analytic in the whole S plane, but it by itself doesn't tell us how it grows as S goes to infinity, right. That's a separate input you have to give.
So another question related to this one, which is this, I mean, sometimes people try to show that, I mean, sometimes people almost, you could ask, if you're interested in the following physical question, are the S matrices consistent with causality? Then I see statements that causality and analyticity are tightly related to each other. So I was wondering whether next, since you've shown that string theory amplitudes are finite, that they all obey unitarity, that they're analytic, I was wondering if your next program is to show that
causality, I don't know, maybe. Okay, one has to first formulate the question, right? What is the question that one should answer, right?
Right. So, but it sounds like it's going to be analyticity plus some growth at infinity.
Yeah.
The two will imply causality, whatever.
Probably. I mean, the growth at infinity, of course, is a tricky this thing, right? I mean, starting from Gross and Mende, I mean, it's. I mean,
it feels like the string theory growth. No, but the Regge limit. It's probably the Regge limit that controls.
Regge limit, okay, yeah.
And that's nice and powerful.
Okay.
So not the e to the power minus.
Okay, but even then, you have to do sum the loops, right?
Sum the loops, right.
I mean, Regge limit at tree level is nice, right?
Right.
We still don't know what happens when you include all the loops.
Correct.
Right?
Correct. Do you know what happens at one loop, for instance? Does it get worse or better?
I don't know. I don't remember.
I mean, our general expectation, I think, is that the full answer should be better than the classical answer.
Yeah.
But the loop by loop, it could be worse.
Yeah, loop by loop it could be. Yeah, you have to already sum.
Right. So maybe it's not causal loop by loop.
Yeah.
It's only the
Yeah.
sum.
Yeah.
No questions?
Yeah.
So all this analysis works for string compact applications.
Yeah, because I never use D anywhere. Exactly. As long as there are a number of non-compact dimensions is larger than 4, right? In D equal to 4, as I said, you cannot even take the zero mass limit, right? Because amplitudes are infinite divergent.
Sorry, let me ask one again. So I'm sorry, big question. If we wanted at very high energies, high energy fixed angle scattering, let's say 2 to 2, I think we would expect that decays very fast to 0. Because at very high energies, what would happen is that a black hole would be formed, and the chance that would decay to 2 particles is basically infinitesimal.
Okay.
Right. So we could probably use classical physics.
Okay.
To estimate the true quantum.
What should be the growth?
What should be the growth for very large angle for fixed angle high energy scattering?
Yeah.
Can we also use classical physics to estimate
Regge?
Or maybe that's completely different regime because it's just like high.
Yeah.
I mean, I don't know the answer.
Yeah, I think Veneziano and his collaborators, they did some calculation, I think, high energy scattering, right? Iconal scattering in string theory.
And that will have nothing to do with black holes?
Well, the point if the impact parameter becomes small enough, then it forms black holes. So I think the point it's an interplay between S and T.
Right, but so now suppose I take S to infinity keeping T fixed.
No, then I think you will form black hole, because if you put very large S, right, the Schwarzschild radius goes up.
Right, but I was wondering whether the B would increase faster.
If you keep T fixed,
because the scattering angle, the ratio
is going down.
So it sounds like you're going further and further.
The angle becomes 0.
0, yeah. So it sounds like you have to go far away.
Maybe no, it's possible. Yeah. But that could also be because of the fast moving particle, no? Angle going to 0. If you have two particles at fixed
distance. Once you go near an event horizon, the scattering angle will be like a light like geodesic.
Okay, yeah, okay. That should be non-zero, yeah, I agree.